All right, so today we are going to be doing a little bit more work with finding zeros. Now, we've already talked about zeros quite a bit throughout chapter classes. We know that if our polynomial is given to us in factored form, meaning we have the parentheses, it's very easy for us to look at those parentheses, figure out the zero, that's going to show us as an x-intercept on the graph. That was a huge part of our graphing process. Well, today we're going to look at how can we find zeros if it's not in factored form to begin with. You'll notice that all four of these problems today are standard form. And so we're actually going to be applying the different skills and strategies that we've been practicing for factoring that we did on block day. We're going to be applying that to our problems today. There's one other little thing that I want you to think about in the back of your mind through this process of finding zeros, and it's called the fundamental theorem of algebra. We're going to start by filling in the statement at the top of the page to see what this theorem says. The theorem states that the degree of a polynomial is equal to the number of zeros that it has. Now, since these ones today are all standard form, we know that to find the degree, it is simply the highest exponent that we see. So, for example, in problem number 1, notice how the degree is 3, so that means it's going to have 3 zeros. It's sort of helpful to think about that at the start so we know how many answers we're looking for. At the end of our process, we know that we have found all the zeros. Now, another thing about zeros is that they're also called roots. That's just a different name for the same thing. You might see that in the directions to a future problem. Some textbooks will use the word root instead of zero. Helpful for you guys to know that it's the same thing. And what they are is they're really just solutions to setting our polynomial equal to 0. And you'll see here in parentheses that we're going to be including both real and imaginary solutions. So the ones that we have seen and talked about so far have all been real zeros because only real zeros show up on the graph as x-intercepts. But what we're going to see now today is that it's possible for a zero to be imaginary. Not a big deal. It just means that it's not going to show up in any way on the graph, but we still need to list it out as one of our zeros to add up to the total of whatever it's supposed to have. Now, one final quick thing about the fundamental theorem. So if something is supposed to have 3 zeros, that's going to be including the multiplicity, which the multiplicity is like the number of times the zero repeats if it happens more than once. So for example, you don't even have to write this down off to the side. I just want you to see it. If we were listing out our zeros and we're supposed to have 3 of them, it could be something like this. It could be 2 is listed twice. We're going to count it twice. 2, 2, and -3. So it doesn't have to be 3 distinct, completely different values. Okay, so let's get into this process here for our first example. So you can see up here at the top, it's a simple method that we're going to follow to find all the zeros. We're going to start by setting y equal to 0, which is a really easy first step. All of these are set equal to y at the very start. And then we are going to use one or more of our factoring methods. We're going to get it factored down as far as we can go. And then once it's factored, we're simply going to set each factor equal to 0 and solve for x. The first thing we're always going to look out for is a greatest common factor. In this case here, it looks like everything can be divided by 2x, so we're going to go ahead and pull that out in front. On the inside, we're going to be left with x squared plus 3x minus 40. Now that leftover part on the inside, we can actually take that a little bit further. it looks like a basic trinomial. So I'm going to do a little bit of thinking off to the side here. We're going to find what multiplies to negative 40 and adds to 3. It looks like we could do positive 8 and negative 5. So we're still going to keep the 2x in the very front, but we're going to turn the trinomial part into 2 parentheses side by side and fill them in just like this, x plus 8, x minus 5. Okay, we have factored as much as we can, so it's time to move on to that third and final step. Every piece that involves an x is going to get set equal to 0, including the 2x part at the very beginning. Now let's be careful when we go back and solve the first one. That x is being multiplied by 2, and the way that we're going to undo multiplication is through division. So we're going to divide both sides by 2, and the nice thing about that is that 0 divided by anything, still 0. That's our first answer. We'll go ahead and subtract 8 from both sides to get the second one of negative 8. We'll add 5 to both sides to get the last answer of positive 5. All right, so the degree was 3. We were supposed to get 3 zeros. This is what they are. These ones are all real, so that means that they would all 3 show up as x-intercepts if we were to graph this. All right, so let's look at the next problem. It looks like this one also has a degree of 3, so we're going to have 3 zeros at the end. We're going to start off the same way. We're going to set y equal to 0. Notice that this one has 4 terms. So we're going to think about factor by grouping. So when we take that GCF out of the first 2 terms, it's that very common x squared that we were talking about earlier, that's common to C. When we take out the x squared, that's just going to leave us with x plus 4. And then out of the second 2 terms, it looks like they both have a negative sign, and they can both be divided by 9. So let's divide a negative 9 out of each one. That is also going to leave us with x plus 4 in the parentheses. We know that the parenthesis part has to be exactly the same. Whatever was in the parenthesis part that was the same, that is how we are going to fill in the first parenthesis of our final answer. So we'll go ahead and fill in the x plus 4 here, and then the x squared minus 9 is going to be listed second. All right, now let's look at x squared minus 9. It is subtraction, and so it is a difference of squares. Let's go ahead and factor that further into x plus 3, x minus 3. You're going to keep the x plus 4, keep it where it is at the very front. Same way to finish this out, we're going to set each part equal to 0. And when we solve for x here, we're going to get negative 4, negative 3, and positive 3. I tend to list them out separately, like I've been doing here, but another way you could write it is you could just write x equals out in front, and you could just list your separate answers, just like separating them with a comma. So it looks like this one has 3 real zeros again. Those are all going to show up as x-intercepts if we were to actually make the graph of that. Okay, let's take a look at the next one. Degree is 3 again, so we should have 3 zeros. This x cubed minus 64 now looks like a difference of cubes. So we can certainly see that x is being cubed at the beginning, but we also know that 64 is a perfect cube. It is 4 cubed. And so what we want to think about here are those Stokes formulas that we did yesterday. Now, when I am applying one of these formulas, I still like to write it out in terms of A and B first. Then I go back and fill in the pieces what they should be, matching the problem. So what I remember from yesterday is that we started with a binomial in front, and then we had a trinomial behind it. I know that inside of the binomial is a regular A followed by a regular B. And then I know inside the trinomial part, it's supposed to be A squared, A times B is in the middle, and we have B squared at the end. Then I'm going to think about SOAP to fill in the symbols. So S, same sign as the original, so because this one is being subtracted, we've got to have a subtraction sign first. O is going to be opposite sign from the original. AP is going to be always positive for that last symbol. All right, so let's go ahead and fill this in. So here, the way that we've written it, we can see that A is going to be X and B is going to be 4. So in the binomial part, it's just simply X minus 4. And then for the trinomial, we're going to have X squared plus 4X. And instead of writing 4 squared at the end, I want you to think about 4 squared in your head, but I want you to go ahead and write it as 16. Now, if we think about like truly trying to factor this as far as we can go, notice that the second part, the trinomial, it looks like a basic trinomial. And so let's go ahead and think about testing our numbers off to the side. If we are able to factor that further, we need to find two values that multiply to 16 and add to 4. Let's think about some possibilities. So what multiplies to 16, we could have 1 times 16, 2 times 8, 4 times 4. It looks like it's not going to work. So it doesn't look like any of those possibilities are adding to 4. So it's one of these. It's one of these where the numbers just don't work for us to factor. That's okay. We've seen this situation before. If you get stuck, so if you're not able to go further, we're just going to go ahead and set our two parentheses parts equal to 0 right now. And let's go ahead and solve that first one because it's going to be so quick and simple for us. So we get one of our zeros, one of our solutions is going to be positive 4. What we really have over here in the second one is we have a quadratic equation that is not possible to solve by factoring. How else could we solve a quadratic equation? Yeah, we could do the quadratic formula instead. That's what the quadratic formula is for. It solves quadratic equations, any quadratic equation, but it's especially helpful if another method like factoring doesn't work. So remember that the quadratic formula is based on the values of A, B, and C. So let's identify those here. We can see that A is 1, B is 4, C is 16. It's been a little while since we have used the formula. So down below, we're going to go ahead and write this out in terms of A, B, and C. And remember, we have our little quadratic formula song that goes along with this. So we've got x is equal to minus b plus or minus square root b squared minus 4ac all over 2a. Pop goes to Weasel is the 2. All right, so I'm going to give you a moment on your own. I want you to fill in the values for A, B, and C. And I want you to simplify your answer down as far as you can go. All right, so initially this is how it looks plugging our values in. So we should end up getting inside of that square root part is really where most of the simplifying is going to happen. It ends up being 16 minus 64. So it's going to go into the negatives because 16 minus 64 is negative 48. What does it mean about this type of answer if it has the square root of a negative? It's imaginary. So for the first time today, we're going to see that our final two zeros are imaginary zeros. That's okay. We still need to include this in our list. We're still going to simplify this answer down as far as we can go. So one thing that we want to do if it's imaginary is we want to get that negative sign out of the square root symbol. So initially we can think about splitting this up into square root 48 multiplied by the square root of negative 1. And that's because the square root of negative 1 is equal to I. And so what that does is it's just going to put a little I on the end, and now we're just dealing with the square root of positive 48. Now, if we were to think about reducing this down, 48 is the same thing as 16 times 3. And that's actually super helpful because we can do the square root of 16. The square root of 16 is 4. Keep that out in front of the square root of 3. So I'm going to rewrite this now as 4 square root 3. I'm still going to put the I at the end. The whole thing is still being divided by 2. All right, now the final thing we can look at, notice how both of the elements on the top can be divided by 2. They both involve a 4. We can actually do that to simplify the final piece down. So taking the first element on the top, which is negative 4, we're going to do negative 4 divided by 2, and that turns into negative 2. And for the next element here, the only part that's going to get divided by 2 is the 4 in front of the square root symbol. That will also turn into 2. The square root 3 part is not touched or changed, and the I does not change either. We're still going to keep those pieces at the end. Now remember that plus or minus sign really represents 2 different solutions. You don't have to write them out separately, but this is really what it would be. So it's the negative 2 plus 2 square root 3i answer. The other one is negative 2 minus 2 square root 3i. Now technically listing out all 3 of our solutions for all 3 of our zeros. Remember we had positive 4. I know it feels like a long time ago since we got that very first one. But that was our first zero, and then we have these other 2 that are imaginary. So what's interesting about this one is that if you were to do the graph, the only x-intercept you're going to see is at 4. And you just don't see anything else for the imaginary zeros, but we know that they're there because we know that it's supposed to have 3 zeros altogether. All right, we just have one final question left, so let's go ahead and continue and finish up with problem 4. Let's go ahead and start the same way by plugging in 0 for y. We have a greatest common factor that we can take out of these 3. They all have a single x in common. And so when you take that one x out, it's basically just going to reduce the exponent by 1 when you're filling in the inside. It's going to turn it into this. All right, now that inside part that we're left with, that is one of those x to the 4th trinomials. So we're going to think about our numbers here. If it works out, it'll factor into 2 parentheses side by side. It's going to have an x squared at the front of each one. And all we need here is for those numbers to multiply to -4 and add to -3. So it looks like that should work out nicely if we do -4 and +1. Now notice that we have a difference of squares. Difference means it has a subtraction. So we can actually turn that into x plus 2, x minus 2. We're not going to do anything with the 1 at the end. You can just leave it as it is, x squared plus 1. We're going to leave the x at the very front. And so once we factor it as far as we can go, we'll continue by setting each part equal to 0. I forgot to say this at the very start, but I wanted to point out that this one is a degree of 5, so we are looking for 5 zeros. Okay, so the very first one is 0. That one was nice and easy. From the second equation, we get -2. And from the third equation, we get +2. All right, so let's talk about what's happening here with this x squared plus 1. Well, let's think about getting that 1 over to the other side. It's going to turn into -1. What can we do to both sides here that's going to get rid of the squared? The square root. All right, so here's a couple of things we're going to think about. Anytime you introduce the square root symbol into your problem, you need to put the plus or minus sign out in front of the result. That plus or minus is what's going to make the count 5 total zeros at the end. We've got the first 3 zeros right here. This is 0 number 4 is the positive version, and then 0 number 5 is the negative version. If you don't have the plus or minus sign in front, you're not going to get a list of 5 zeros. You're going to be missing one, and you're going to be confused. So make sure that you've got the plus or minus sign there. And then we actually have something special here. Is there another way that we could write the square root of -1? Like a symbol. Do you remember, Acton?
1i.
It's I. Yes, exactly. 1i, or you can just say I. And that's the definition of I. So I'm going to write off to the side here. So we're going to remember that the square root of -1 equals I. So the last 2 zeros are just imaginary. So if we were to list out all 5, like in a list, so it looks like we've got 3 real zeros at the start. Those are going to be x-intercepts on the graph. We've got positive I and negative I. To get the 4th and 5th zero, those ones are not going to show up on the graph, but we still have to include them in our list of zeros.